When you build software on your own machine, you are working in a perfectly isolated environment. Everything behaves exactly the way you tell it to. You confidently run through your final checklist. The user authentication passes, the APIs respond correctly, the database connects instantly. You look at the green checkmarks and declare the application production ready. But there is a flaw in this approach. You designed every single feature for success. You wrote the code assuming the network would always be fast and the data would always be there. A local machine is a controlled vacuum. The internet is chaotic. Out in the real world, cloud providers experience outages, external servers crash, and cellular networks drop out mid-request. Failure isn't a possibility, it is an absolute guarantee. Surviving that environment requires a complete shift in how you build systems. Based on 10 hard-earned lessons in production engineering, making software work is entirely different from making it keep working when things go wrong. You launch the application, real users begin to log in, then a third-party authentication service you rely on suddenly drops offline. This flowchart shows what happens when you ignore failure paths. A single API request hits a dead end at the primary database. Because the application doesn't know what to do next, the server hangs waiting for a response. Memory fills up, and the entire system crashes. To survive this, you build in fallbacks. When the primary database fails, the request is instantly routed to a secondary path. The system gracefully degrades, serving up older cached data so the user still sees their screen while the main service recovers in the background. A major part of that defense mechanism is caching. Querying a fragile database every single time a user loads a page is slow and computationally expensive. Storing that exact same information in memory, where it can be retrieved instantly, saves time and drastically reduces the load on your servers. Without these fallbacks in place, a glitch in an external network immediately becomes a fatal error in your own application. Let's assume you survive the initial launch. The app gets popular, traffic spikes, and a massive wave of users hits your servers all at once. This diagram illustrates a standard user interface asking for data. If your front-end directly requests a user profile, recent posts, followers, notifications, and messages all at the same time, it opens 5 separate connections. You just multiplied the chance of a network timeout by 5. The solution is an architecture pattern called a backend for frontend, or BFF. Instead of 5 fragile calls, the front-end makes 1 clean request to the BFF layer. The BFF handles the messy orchestration internally, gathering all the data across your microservices instantly and passing it back as one neat package. As your traffic doubles, a single server will inevitably choke under the pressure. Scaling out across multiple servers behind a load balancer isn't a feature you can easily bolt on later. It is a structural foundation you have to plan for from day one. Rapid user growth subjects every architectural shortcut to a brutal stress test. Even with solid architecture, you still have to defend your application against the most unpredictable variable of all, human beings. If your APIs accept unlimited requests, a malicious bot can flood your servers with 10,000 calls a second until they crash. Setting up rate limiting shields your application by strictly capping how many times a single user can ask for data in a given window. Here, we see a logic gate visualizing a concept called idempotency. Normal users make mistakes, like frantically double-clicking a payment button. Idempotency ensures that when 2 identical payment requests enter the system, it checks for a duplicate ID, processes the first charge, and safely nullifies the second one without throwing an error. And when you release new code, bugs will eventually slip into production. You mitigate this with feature flags, remote kill switches that let you disable broken components instantly, alongside deep observability metrics that log exactly where and why the error occurred. You have to engineer defensively around human unpredictability, because you cannot fix a disaster you cannot observe, and you cannot stop a broken feature if you can't instantly disable it. The moment code reaches production, the focus shifts from writing features to the active, ongoing discipline of production engineering. When you write code, you ask, how do I make this work? But when you maintain a live system, your primary question becomes, what happens when this fails at 2 a.m. while I'm sleeping? End users do not care if you use the most sophisticated cloud architecture available. They care that the application actually loads when they need to use it. Software is about building trust. In a live environment, failure is a guaranteed expectation. The systems that survive are the ones built from day one to anticipate their own destruction.